Dear students, how are you? In today's module, we will see about group of symmetrics. In previous modules, we briefly discussed the concept of symmetric group and to know how to form a Cayley table for this group. From this module, we can understand the definition of permutation, definition of symmetric group with rational property and the important subgroup of symmetric group called alternating group also briefly explained here. Learner can learn a lot from this module and it will be very useful for your further studies definitely. What is permutation group? A permutation of a set A is a function from A to A, that is both 1 to 1 and on to. A permutation group of a set A is a set of permutations of A that forms a group under function composition. For example, we define a permutation alpha of the set 1, 2, 3, 4 by specifying 1 alpha is equal to 2, 2 alpha is equal to 3, 3 alpha is equal to 1, 4 alpha is equal to 4. A more convenient way to express this correspondence is to write alpha in array form as alpha is equal to 1 goes to 2, 2 goes to 3, 3 goes to 1 and 4 goes to 4. The symmetric group is important to diverse areas of mathematics, and the symmetric groups on infinite sets behave quite differently from symmetric groups on finite sets. These are discussed by Scott in 1987. Afterwards, Dixon and Mortimer Cameron also discussed in 1996 and 1999 respectively. Symmetric group Sn. Let A is equal to the set 1, 2 and so on n. The set of all permutations of A is called the symmetric group of degree n and is denoted by Sn. Elements of Sn have the form like this. See here, alpha is equal to 1 goes to 1 alpha, 2 goes to 2 alpha and so on, n goes to n alpha. It is easy to compute the order of Sn. There are n choices of 1 alpha. Once 1 alpha has been determined, there are n minus 1 possibilities for 2 alpha. Since alpha is 1 to 1, we must have 1 alpha which is not equal to 2 alpha. After choosing 2 alpha, there are exactly n minus 2 possibilities for 3 alpha. Continuing along in this fashion, we see that Sn must have n into n minus 1 into 3 into 2 into 1, nothing but product of first n natural numbers which is equal to n factorial elements. In previous module, we already proved that the symmetric group Sn for n is equal to 3 is non-abelian. So, we leave it to the reader to prove Sn is non-abelian when n is greater than or equal to 3. Next is definition of symmetric group through rotation. In group theory, the symmetric group of a geometric object is the group of all transformations under which the object is invariant, endowed with the group operation of composition. Such a transformation is an invertible mapping of the ambient space which takes the object to itself and which preserves all the relevant structure of the object. Let us see the geometrical view of permutations in symmetric group. We will now see that the group of symmetrics of the square also forms a group with respect to the operation of composition. Consider a square and label the vertex 1, 2, 3 and 4. Keep these labels fixed for reference. We may describe a 90 degree. We will explain this by the diagrammatic view. See these pictures. Let row 0, row 1, row 2, row 3 from the set 1, 2, 3, 4 mapping to the set 1, 2, 3, 4 be functions that represent the rotational symmetries. Let mu1, mu2 from the set 1, 2, 3, 4 mapping to the set 1, 2, 3, 4 be functions that represent the perpendicular bisector axial symmetries, and let delta 1, delta 2 from the set 1, 2, 3, 4 mapping to the set 1, 2, 3, 4 be functions that represent the diagonal bisector axial symmetries. Each of these functions can be described as a 2 by 4 matrix where the first row lists the original arrangement of the vertices on the square and the second row lists the change in the positions of the vertices after the particular symmetries are applied. We have that row 0 is a identity permutation and row 1 is a rotation with respect to identity permutation. So, here 1 goes to 4, 2 goes to 1, 3 goes to 2 and 4 goes to 3. Similarly, for row 2 and row 3. Next, for mu1, take an axial flip along a perpendicular bisector respect to identity permutation. So, 1 goes to 4, 2 goes to 3, 3 goes to 2 and 4 goes to 1. Similarly, for mu2 too. And for delta 1, take an axial flip along a diagonal bisector over identity permutation, which is a mirror image over diagonal bisector. So, here 1 goes to 1, 2 goes to 4, 3 goes to 3 and 4 goes to 2. Similarly, for delta 2. See here, row 0 is equal to 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. Row 1 is equal to 1 goes to 4, 2 goes to 1, 3 goes to 2, 4 goes to 3. Row 2 is equal to 1 goes to 3, 2 goes to 4, 3 goes to 1, 4 goes to 2. Row 3 is equal to 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. Mu1 is equal to 1 goes to 4, 2 goes to 3, 3 goes to 2, 4 goes to 1. Mu2 is equal to 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. Delta 1 is equal to 1 goes to 1, 2 goes to 4, 3 goes to 3, 4 goes to 2. Delta 2 is equal to 1 goes to 3, 2 goes to 2, 3 goes to 1, 4 goes to 4. Now, we are going to see these permutations in different manner. That is nothing but a cycle notation. There is another notation commonly used to specify permutations. It is called cycle notation. As an illustration of cycle notation, let us consider the permutation. Alpha is equal to 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 6, 5 goes to 5, 6 goes to 3. The assignment of values presented schematically in this way. See these diagrams. In simple without arrows, alpha is equal to 1 goes to 2, 2 goes to 1. It creates a cycle. 3 goes to 4, 4 goes to 6, again 6 goes to 3. It forms a cycle. 5 goes to itself, it creates a cycle. Here the notice an expression of the form alpha 1, alpha 2, alpha m is called a cycle of length m or m cycle. Two cycles are said to be disjoint if they have no element in common. We know that every group should have an identity element. So, here the identity of permutation is identity permutation. The identity permutation consists only of cycles with one entry, so we cannot omit all of this. In this case, one usually writes just one cycle. For example, alpha is equal to 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5. Could be written as alpha is equal to the cycle 5 or alpha is equal to the cycle 1. Or just remembering that missing elements are mapped to themselves. Next, we will see some important properties of permutations. Every permutation can be uniquely expressed as a product of disjoint cycles. Cycle of length 2 is called transposition. A permutation of a finite set is even or odd according to whether it can be represented as the product of an even or odd number of transpositions respectively. Identity permutation is an even permutation. The inverse of an even permutation is even, and the inverse of an odd permutation is an odd permutation. Now let's see some results. The result 1 is any permutation of a finite set can be expressed as a product of transpositions. Let us prove this. Consider the cycle x1, x2 and so on xr. A computation shows that x1, x2 and so on xr is equal to x1, x2, x1, x3 and so on x1, xr. Therefore, the assertion of the theorem is true for cycles. Now, since every permutation is a product of disjoint cycles and every cycle is a product of transpositions, it follows that any permutation is a product of transpositions. Now, let's see the result 2. The product of two even permutation is an even permutation. Let's justify it. Let theta 1 and theta 2 be two even permutations. Choose one way of writing each as a product of transpositions. Then, theta 1 has 2i transpositions and theta 2 have 2j transpositions. Their product has a total of 2 into I plus j transpositions and is therefore even. Next, we see the result 3. The product of even permutation and an odd one is odd. Likewise, for the product of an odd and even permutation. We will justify it without loss of generality. Let theta 1 be odd and theta 2 be even. Choose one way of writing each as the product of transpositions. Then, theta 1 has 2i plus 1 transpositions and theta 2 has 2j transpositions. Their product has a total of 2i plus 1 plus 2j. Here we will take 2 as the common factor. So, 2i plus j plus 1 transpositions and is therefore odd. Next, we will see the fourth result. The product of two odd permutations is an even permutation. The justification is, let theta 1 and theta 2 be two odd permutations. Choose one way of writing each as a product of transpositions. Then, theta 1 has 2i plus 1 transpositions and theta 2 has 2j plus 1 transpositions. Their product has a total of 2i plus 1 plus 2j plus 1. Here 1 plus 1 is equal to 2. So, common factor, the 2 will be taken outside. So, 2 into I plus j plus 1 transpositions and is therefore even. Okay, let us see some problems now. The problem 1. Determine which of the following even permutations are. A. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1, 6 goes to 6, 7 goes to 7, 8 goes to 9, 9 goes to 8. The next sum is the cycle of 1, 2, 3, 4, 5, the cycle of 1, 2, 3. Let us see the solution. We will express the given permutation as a product of transpositions. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1, 6 goes to 6, 7 goes to 7, 8 goes to 9, 9 goes to 8 is equal to the cycle of 1, 2, 3, 4, 5 because again the 5 goes to 1. So, it creates a cycle. Here the 6 goes to 6 itself. This is a cycle of 6. And 7 goes to 7 itself. It's a cycle. And 8 goes to 9. 9 goes to 8. It's a cycle. So, here we will get the answer as the cycle of 1, 2, 3, 4, 5 and the cycle of 8, 9. So, now we have to find it is odd or even. So, this cycle will be converted as the transpositions. The cycle 1, 2, 3, 4, 5 will be converted as the transpositions. How? The cycle 1, 2, the cycle 1, 3, the cycle 1, 4 and the cycle 1, 5. Already we have the cycle 8, 9. Since there are 5 transpositions in the product, the given permutation is odd. The next sum is the cycle 1, 2, 3, 4, 5 and the cycle 1, 2, 3. So, we will convert this cycle as the transpositions. We will get the result as the cycle 1, 2, cycle 1, 3, cycle 1, 4, cycle 1, 5 and the cycle 1, 2, cycle 1, 3. Since there are 6 transpositions in this product, the given permutation is, yes, you are right, it is even. Next one is the subgroup of Sn, that is alternating group. A permutation theta belongs to Sn is said to be an even permutation if it can be represented as a product of an even number of transpositions. Let An be the subset of Sn consisting of all even permutations. Since the product of two even permutations is even, An must be a subgroup of Sn. An is called the alternating group of degree n. The order of An, it will be denoted like this, is equal to n factorial by 2. Sn has n factorial elements. An is having only even permutations. So, order of An is equal to n factorial by 2. Based on the subgroup An, let's see the upcoming remark. Since An is a subgroup of Sn of order n factorial by 2, the index of An in Sn is order of Sn by order of An is equal to n factorial by 1 by 2 n factorial is equal to 2. But any group of index 2 in a group G is normal in G. Therefore, An is normal in Sn. Both Sn and An are very important groups. Note that the set of all odd permutations in Sn is not a group, since the product of two odd permutations is even. Hence, half the permutations of any symmetry group Sn are even and half are odd. Sp is equal to D6. Dihedral group of order 6 is the smallest non-abelian group. Finally, let us see the next problem for our clarification towards An and Sn. The second problem is, write down all the elements of S4 and A4. The solution is, S4 contains 4 factorial elements is equal to 24 elements. They are identity, cycle 1, 2, cycle 1, 3, cycle 1, 4, cycle 2, 3, cycle 2, 4, cycle 3, 4, cycle 1, 2, 3, cycle 1, 2, 4, cycle 1, 3, 2, cycle 1, 3, 4, cycle 1, 4, 2, cycle 1, 4, 3, cycle 2, 3, 4, cycle 2, 4, 3, cycle 1, 2, 3, 4, cycle 1, 2, 4, 3, cycle 1, 3, 2, 4, cycle 1, 3, 4, 2, cycle 1, 4, 3, 2, cycle 1, 4, 2, 3, cycle 1, 2, cycle 3, 4, cycle 1, 3, cycle 2, 4, cycle 1, 4, cycle 3, 2. The product of the cycles 1, 2 and 3, 4, product of the cycles 1, 3 and 2, 4 and the product of the cycles 1, 4 and 3, 2. A4 is the set of all even permutations in S4 and it contains 4 factorial by 2. 4 factorial is equal to 24. So, 24 by 2 is equal to 12 elements. They are identity, cycle 1, 2, 3, cycle 1, 2, 4, cycle 1, 3, 2, cycle 1, 3, 4, cycle 1, 4, 2, cycle 1, 4, 3, cycle 2, 3, 4, cycle 2, 4, 3, product of the cycles 1, 2 and 3, 4, product of the cycles 1, 3 and 2, 4 and the product of the cycles 1, 4 and 3, 2. Okay students, we have come to the conclusion of this session. Through this module, we have understood the concept called symmetric group and its subgroup alternating group. Geometrical view of this concept also briefly explained, and the very important properties with their examples are effectively discussed in this session. Okay, we will see in the next session. Thank you very much.